Hello and welcome everybody to Advent of Code 2023, day 14. So I'm coming at you for the second time today. We talked about day 13 this morning. So now I finished day 14. So let's have a look at that. I might keep going and I might try and finish off day 12 part 2 as well, but we'll see. let's not do anything crazy here. All right. With that said, let's jump into this problem and have a look at what we did. So, actually, first of all, I should say this was quite a fun problem today. There was kind of some interesting stuff in it. There's always seems to be always a problem every year where there's something to do with like it's almost like a graphical thing that you have to do some translations on it. And then they ask you, and now do it a million times or do it a billion times, which is what they did here. I think they did almost the exact same thing last year. There was like a something that was like Tetris last year that was sort of building up this massively long tower. And eventually, and it was like, well, what'll happen if you do this a billion times? So you can't simulate that a billion times. But the trick with that one, and it's the exact same trick that's in this one, is that it's a repeating pattern. So all you have to do is simulate it enough times to fully cover the repeating pattern, and then you can use like a little bit of maths basically to figure out what the answer should be. So with that said, let's have a look at how I did these two parts, because I actually did them differently. Part one I did in a relatively naive way. It was quite elegant for what it was, and I was really hoping they weren't going to do the second part like I described, which is what I suspected they might do. Turns out they did, so I ended up having to basically rewrite my solution for part two. So in part one, I don't actually simulate the movements, I just sort of do an inference to get the answer. And then for part two, I ended up doing all the simulation, but I did some clever optimizations to make it run efficiently. Yeah, the cat thinks they were clever too. So, right, finally, with all that said, let's talk about the problem and let's look at the code. So, day 14, parabolic reflector dish. So, in the last puzzle, we were going through this valley of all these mirrors. So, you end up finding that there's, through the valley of all the mirrors, you end up with this like finding this parabolic reflector dish thing, and you think that there's a bunch of them, and you think that if they're all focused properly in the right point, that's what's going to make the lava that will generate the heat that we need. So what you figure out is you find this mechanism that has all these pulleys and ropes and a bunch of rocks on it, and depending on what way the mechanism is tilted, the rocks move from one side to the other, and that basically changes the orientation of the mirror. So that's what we're trying to do. So our input for the puzzle is basically this thing here. So this represents like our table. If you can imagine, it's like a flat table, and it can tip forwards, backwards, left, and right. And the symbols mean some different things. So the dots just mean empty space. The hash symbols are rocks that are like fixed in place, they don't move. And then the large O's represent boulders that can roll around basically as you move. So it's not explicitly stated, but it is assumed that basically each boulder can only move up or down or left or right in its place, so they don't roll diagonally or anything like that. And yeah, our planes just tip forward, backwards, left, and right. So what they ask you to do for the first part is they ask you to... Oh, and also you can then calculate the weight that this is putting on the support that it's holding it up by some maths thing that he defines yet down here. So basically what this means is, so you're trying to determine the weight that this rock is placing on the beam that it's like pressing against, whatever the support structure is. So the way you work it out is each of these is worth 1 unit of weight. So it's 1 unit for all of these times 10. And then as you get further away from the top, they reduce by 1. So these two are both worth a value of 9. So that's 18 for that row, and then so on and so forth as you go the whole way down. So that's just how you calculate the weight, basically. And that's ultimately what they want. So you start off with this pattern, and then they say if you tilt it forward, So all the rocks will basically roll up the plane. You should end up with some pattern that looks like this. So you see the rocks will basically move through free space unless they hit a stationary rock, or they hit the end, or they hit a rock in front of themselves. And yeah, that'll be it. So you tip it the whole way and they'll roll the whole way down. And then once they're in that position, you calculate the weight. So that's what we're asked to do. So we're told for the first part, tip it north. So tip the front bit down, let them all roll, and then calculate what the weight is once they've all rolled. And that's all we're told to do for the first part. So this is where I was really hoping that they weren't going to say, and now tilt to the left, and now backwards, and then right. But I implemented an IU solution because I thought, well, maybe there'll be some other way they'll change it. I should have seen it coming. But anyway, let's have a look at my part 1 code, because it is substantially different to the part 2 code. So part 2 code is where we'll really get into the nitty gritty of the difficulty of this solution. So let's have a look at part 1. So you see, I said it was elegant. It is quite short. It's quite nice. So what I do here is I start off. So I figured that for this problem, all I'm interested in is each vertical line of rocks, or what makes them up. So in my parsing code here, I go through the file and I essentially extract just those vertical lines. I do something in here where I replace all of the dots with nil. So it's like null in Ruby. And that is important in a second. And yeah, so I end up then with this array of arrays, a 2-dimensional array, where each sub-array is just a vertical, is a representation of each vertical as you go along. So what I do then to determine the weights, instead of simulating the movement, what I decided to do was I decided to so I missed one other bit. So my idea was, explain the rough idea first that I had was, well, if we have this array of all these rocks and stuff, as they roll up the way, or so as they roll north, what's going to happen is all of the blank spaces are going to get filled completely, or they're going to get filled completely, or they're not going to get filled because they're going to have been behind a rock. So what I mean is, if you look like in this line here, so this one moved all the way to the end, but because there was this rock here, these two didn't, but they moved all the way up. So what happens is, like, all these spaces are they're effectively, they don't matter anymore. They sort of disappear, and the same with these ones. So what I used was I thought, well, if I use the compact operation in Ruby on an array, what the compact operation does is it goes through the array and finds wherever there's a nil value and it gets rid of it. So all I'm going to be left with if I do that is like round boulder, stationary boulder, round boulder in a row. So what I decided to do with that is I decided to encode into this, into the original data, what the symbol was and what index it originally had. Now, what happens then is, as I talk through this, I realize this, although it might be kind of clever, it's actually a stupid way to do this. So I'm now looking at an individual vertical array. I take all those rocks, I do the compact operation, so now it's just the original rocks encoded with their original positions. Sorry, now it's just the rocks encoded with their original positions. So I start from the first one, and I do this sort of lookup thing here based on a hash symbol, based on finding a hash symbol. So if you find a hash symbol, you change this ID value. So the ID value starts at 0. You change this ID value to equal the ID of that stationary rock. Because like they're all going to slide up the way. If you start at 0, so this is the case here. So these rocks all slid up the way. So I started at 0. So I know this rock here is going to be 0. So I have that. I found the rock there, and I go, okay, great. So that will be whatever weight it's going to end up with. So it's like 10 times this 1. So then I keep looking down the way. So now, well, in my code, these dots are all completely gone now. So I just look at I find a stationary rock now. So now that I found a stationary rock, I need to update the ID. So the ID now is going to be whatever that original ID of that stationary rock was. So in this case, it's what, like 6, 1, 2, 3, 4, 5, 5. So it'll be ID 5. Index A5 is my ID now. So then I move to the next one and I encounter a rock. So what will happen is, well, I know, because they all slid up the way, I know that it's going to be whatever is the next ID is. So it's ID was 5, so the time it loops, ID is now 6. So we're basically just jumping blank space. That's actually an easier way to explain this. When we do that compact operation, every time we find a new stationary rock, we've jumped all the blank spaces where there were no round boulders. And that's it. So then you go through all those, and then you can calculate the weight here based on the total size minus that ID, and then you just append them all. And then at the very end, you stick all the weights in, so I have an array of all the weights, and then I just sum them all together, and that gives you your answer for it. Which I think is clever, but it's not. It doesn't help you do the second part necessarily. So if I run that, it runs. That's the sample. Yeah, it's the sample. So it runs in 90 microseconds, quite fast. There's no real simulation involved. When I run it on the large input, it's pretty fast because there's no actual simulation involved here. Really, it's just parsing the data and then just looping through the columns just to sum all together all those values. That's pretty decent. I'm pretty happy with that, but it doesn't help you solve part 2. So let's have a look at what we have to do for part 2. So go back to our problem. For part 2, we're told that, so you're pushing it around and you still don't know if you're getting the right position. We see this button called spin cycle, this is what I was dreading, that they were going to tell us to now move it left, right, blah, 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 all the ways. So effectively, they tell you that there's these cycles that it can spin through. So it can go forwards, then go left, backwards, and right. So they say it's north, west, south, and east, revolving like that. So what they say is that after one cycle, they give you an example of this is what your output would look like. After 2 cycles, this is what your output looks like. After 3 cycles, this is what your output looks like. So what they want to know is, so you go, effectively what they say is move forwards, right, backwards, forwards, left, backwards, right. Do that once and then see, well, what's the weight now? Because all the boulders have shuffled around. What's the weight now that we have, or the total load value that we calculated? Then do it again, and then do it again, and then do it again. And what it wants you to give the answer is, well, what would happen? What's the answer after you've done this like 1 billion times, or whatever that number is? Is that 1 billion? I don't know. Anyway, that's what they want you to do. So you can't really simulate that. Even if you have very efficient code, just a brute force of that simulation isn't going to work very well. But you don't need to do that at all. So, but anyway, in our case, because I didn't write the simulation code for the first instance of it, I had to fully rewrite it with simulation code and then determine the pattern of how I was going to solve it. So first of all, let's just have a look at the simulation code, because it's not terribly hard. Like, this whole thing is only 100 lines long or so. But yeah, it's a little bit fiddly. So we can ignore this stuff for now. So the first thing I've done is I've made a 2-dimensional array. I've padded extra hashes to the ends of these, and also a strip of hashes across the top and a strip of hashes across the bottom. So that just means the grid we're looking at is like fully bounded by the immovable rocks, which is handy because it means that the algorithm doesn't have to do any funky stuff checking its end positions. But also you have to remember that when you're calculating the weight, I don't know if I mentioned that earlier, actually, the stationary rocks don't count towards the weight. It's just the rolling rocks that count towards the weight. So it won't change the answer if you pad all these extra extra stationary rocks. So effectively, I've written, so I'm going to talk about what this code does in here in a second, but the first part is to look at, well, okay, we need to simulate a cycle, and then we also need to be able to calculate the total load of any given grid that we're given. So let's have a look at our cycles. So our cycle is another subarray thing, it's just a set of operations you have to do. So we know a cycle is forwards, left, backwards, right. So in my code, I've got two methods that do, so we have vertical tilting, which is the back and forth, and we've got horizontal tilting, which is left and right. The reason why they're in methods is because they do slightly different things. Very similar code, they just do slightly different things. And the only difference between them, there's a simple Boolean here, which indicates whether it's a vertical tilt, forwards or north or south, and then a horizontal tilt, east or west. Just a Boolean that defines the difference between them. So this is basically how I get the pattern. And we'll just look at one of these because it's the exact same logic. It's just flipped for the other side. So effectively, the way we get the way I've simulated this is you go through. So you're going to start at the top corner, say, of one of them, and you're going to have a look at. So we'll go for, say, the north case. So we're going to start at the top corner, and we're going to look at all of the spaces that are down below it. So if you encounter an empty space, which is what this first check does, we're going to say we have this array of free slots, which in this instance is going to be a queue, basically. So arrays in Ruby, because there's a bunch of convenience methods written from them, they can work very well to model stacks or queues. So you can basically, an array in Ruby can be a stack if you shift and unshift only from it, and then it'll be a queue if you append to the end and then unshift from the front. So it works quite well. So yeah, we're gonna take our little queue here of our free slots, and we're gonna append to that. If we find a boulder, a stationary boulder, we're gonna clear out any free slots that we currently have. So the next really important part then is if we encounter a boulder or a movable boulder and we have some free slots, then we're going to do something. If we encounter a boulder and there's no free slots below us, so that this is effectively the case where there's just a bunch of boulders stacked against each other, we can't move, there's nowhere to roll into, so the boulder is going to stay stationary. So if we have a free slot somewhere below us and we encounter a boulder, what we do is we replace that free slot that we had. So we use the shift operation to pull the first free slot that we encountered. We stick the boulder into it. We replace the current position with a free slot, and we update our queue of free slots with that existing position. So that might seem a little bit convoluted, but that is effectively the logic. So I was like, oh, I've got a free slot, I have another free slot, I have another free slot. Oh, I have a boulder. I should move that one to the first free slot that I had available. So effectively it'll slide through the other two and hit that first one. And then the same thing for any subsequent boulder. Then if I encounter a stationary rock, it doesn't matter if I had any free slots below it because they're not accessible anymore because the rock can't roll over that stationary boulder. So that's it. So effectively using that logic, that lets you slide all of the round rocks up the board. But also basically the exact same logic lets you slide them left, lets you slide them right, or lets you slide them down. And it's quite simple how it does it, how the difference in it. Because it's a 2D array, if you just flip the indexes around and also flip the directions around, you'll get your two different sets. That's really it. So the only reason I've got two methods to do this instead of one is because there's a little nuance down here where you're what number you use to oh, actually, could I? Actually, I could have refactored this all to be in one. I'm just looking at it now. There is, I definitely could have refactored this all to be one. But it doesn't really matter. The difference is there's a Boolean here that just flips whether you go from 0 to the end or you go from the end to 0. So it's just changes the direction. And then the tilt is changed by basically what the only difference in the tilt is which index it is you're looking at to store the free slots, in the way I've modeled it anyway. But I'm fairly certain I could actually refactor that to all be the same. But anyway, doesn't matter. Let's move on. So we know we can simulate our tilts now, so that's fine. So I can do that. I can simulate tilts, or I can simulate cycles until the cows come home. But I need to also check the values of the cycles when they come out. So I have this algorithm, this little loop written here, which checks the total weight of a cycle. It's fairly simple. It basically takes each horizontal line, because the first line is going to be worth anything in there that's a round boulder is worth 10. Then the next one, anything is worth 11, anything is worth 8, blah blah blah. So for the top one, it'll all be worth, you figure out the number of round boulders you have in there, you multiply that by the index value 10, 9, blah 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 blah, and that gives you you sum them all together at the end, and that'll give you the weight. So that's how we calculate the load. So now, finally, onto the actual meat of the problem. So we can figure out a cycle. We can figure out what we're left with after a cycle. We can calculate the load for that cycle. So now we have to figure out what would that be if we do it 100 million times, or whatever that massive big number is. So the first trick is you don't need to do it 100 million times. The second trick is you just have to know that there's a repeating pattern in here. And that's the only way you could really solve this problem, is if there was a repeating pattern. It might not be obvious to you if you've never seen this type of problem before, but I just happen to know that, based on exactly, because this came up last year, that there's going to be a repeating pattern. It's something you should check if you're ever asked to do something wild like this. Like, just do it 100 million times. You should see, is there a pattern that you can exploit? So the way I exploit this pattern, so you could do it, there's a couple of ways you can do this. If the number was a sensible, smallish number, you could brute force it using caching. I used caching, but I also used it to help me determine what the looping patterns were. So what I've done is, so you'll notice during the code as I talk through it, I have these two caches. I have a tilt cache and I've got a load cache. So the tilt cache is basically, so this algorithm to do the tilting, it's not necessarily the fastest thing in the world. It's not super slow, but if I have to do this like loads and loads of times over and over and over, I don't want to have to compute it every single time. And because I'm fairly certain there'll be a repeating pattern, I can start caching those positions. So what I do is, effectively, I make this cache key, which is just going to be, I flatten out the entire grid. I just flatten it out into a string. And I say, well, if I've already seen that before, I know what the next grid should be if I've already calculated it once. And that's what will happen. So you'll continue to repeat over and over and over again. So those patterns will be, effectively, there's a unique amount of patterns that you'll get, and they'll just keep repeating. So if you've seen one and you've computed it, you know what the answer is going to be, as in what the next pattern is going to be once you've adjusted it. So you don't need to keep doing it. And the same thing is true with the load. Once you've seen a grid before and you've calculated its load, you can store that with the same kind of cache key, and you're only going to get a certain number of those weights, or those loads are going to come out each time. So with that in mind, we can pick some arbitrarily big-ish number, and we can run our cycles and calculate our weights that number of times with the cache continually updating, and basically just sort of see what we get out of it. So that's a lot of that. This stuff down here, these numbers are all basically manual. So this whole calculation down here is effectively, so the calculation part is sound, that works. But these numbers here that plug into this calculation, these were found ostensibly, they're basically found manually by looking at the data that we're getting out of it. So I do a couple of things to figure out these numbers. First thing is, I want to just print out the contents of my cache as I run for some arbitrarily large time. So I'm actually going to do something here as well. I'm going to put in a breakpoint here, and I'm just going to talk through. I'm just going to talk through what happens when we run this. So I'm going to run it for my input instead of running it just for the sample, because actually I'll run it for the sample because that's the same for everyone. So yeah, let's do that, and I'll talk through it. I won't then talk through it exactly for my input. So run it for the sample. Oh, okay, and that went really fast. But what you notice here is you see these cache counts. They're all the same, and they are all the same if you scroll way back here. So yeah, you don't have to go very far because the sample, the loop is very, very small. So you don't have to go very far until you're 100% certain that you've exceeded until you basically haven't found anything new anymore. So in this case, it's down here around, so it's like, this is where we're stopping seeing anything new happening. And this is quite a small amount of iterations. So basically what this tells us is everything beyond this is has been seen already. So we don't really need to go any further than that. The 200 in here is for my input. But in this case, it's quite small. So what I can be fairly certain of now is that somewhere in here, in all of the, so I'm storing every single weight. So I'll have 200 weights stored. And then I also have an occurrences thing here where it's a hash where I store each weight and then I increment the amount of times I've seen that weight. That'll become important in a second. So what I need to figure out is, I need to try and figure out how long the repeating pattern is. And then I need to figure out, well, okay, if I know how long the repeating pattern is, I can add those up until I get to 100 million and then see what's the remainder that I have. There's only one other thing that I need to know, which is I need to know when the repeating pattern starts. The repeating pattern probably doesn't start from your first record. There's probably some offset, and then the repeating pattern starts from there. So you might go 1, 2, 3, 4 records, and then my repeating pattern starts over and over and over again. So with all the other information known, that's what it gives me, these two things. I get the offset and I get the pattern length. Then this little bit of calculating down here using modulus and stuff will give me the remainder of what's left, and then I can use that in here to figure out what it should be. So let's have a look then at what we have here. So if we look at my occurrences hash that I have, so we see we have a whole bunch of numbers here. Notice we've got 87 only appeared once, but then the rest of these numbers all appeared quite a large amount of times. So these numbers all appeared the same amount of times. Then these two numbers happen to appear quite a lot as well. So what this tells me is, as I look through this list, the first number in this list that appears quite a lot or appears many times is probably the first number that my repeating pattern starts at. So let's then have a look at, let's have a look at what were all the weights that I had. Oh, sorry. Okay, sorry. There's something I do here where I basically trim this down. But sure enough, anyway, so this will be part of the repeating pattern. So there's some amount before this, and then there's some amount after this. So actually, you know what I'll do? I'll just move this breakpoint to before I do that so that you can see it. Let's just start that again. Okay. So yeah, so these are all the weights. So this is 200 weights that I calculated 200 times. So there's our 87 at the start. Suspiciously, it only appears once. Then I've got a 69 appears. And then I've got another 69, another 69. What happens to be the case is, in this case, this is the start of our repeating pattern. And it goes down to here until we hit 69, 69 again. So I saw 87, I saw 69, and then this pattern, 69, 69, 65, 64, 65, 63, 68, continues to repeat over and over and over again, ad infinitum. So I know that my offset is 2. I know that my pattern length is 7, because that's how many characters I have here. Hence 2 and 7. And that's all the information I need to be able to calculate what the full answer is, which is you do this modulus operation here. So you take the offset away from the total count. You do a mod with the pattern. That gives you this remainder. In my case, I do this thing. I just take these and I shift them out. I just, basically these operations, these array operations will just give me it'll drop everything else from this array except for the first instance of what the loop is. And then this ID that's calculated from this will be the index of where we would be if we did this 100 million times. Okay. I feel like this is kind of abstract. I hope I've explained it well. I hope if you've never seen this before that this makes sense. But yeah, this is effectively how it works out. And this works for my input as well. It's just a little bit larger. So yeah, I'll do it for my input too. Why not? So for my input, you see it's running much longer before it hits a point, and it has hit that point, which is here. So we got to, so it's somewhere, so it's a 125. It is in my case, but what was this is 125 in my case. Excuse me, but can't remember. Lost my train of thought. Anyway, let's look at the numbers. That's what I wanted to show. That's what I wanted to say. We'll have a look at the occurrences. So if we look at the occurrences, so we see we have a lot more values in here, and we see a lot of ones. So these are patterns these are numbers at the very start that we're seeing just once. So we keep going, keep going, and keep going, and keep going, and keep going, and eventually we'll get to a number. Oh, there we go. So here's a number that has appeared more than once. So it's the first number that's appeared more than once. It's reasonable enough to assume that that is probably our starting number. So we can have a look at this. So 93683. So then if we look at our weights, so it's long, but we go down through this list and look for 93683. 93, have we passed it already? Oh no, we haven't, sorry. 93683. Yes, these are all descending as it happens. Yeah, so there we go. So there's 93683. And by some inspection, you can sort of scroll a bit and you will find that 93683 repeats again. So there's 93683. So if you scroll up and find where the first one is and count the difference, the pattern length is 26. And then if you scroll up and find that original instance again, 93683, and you do just check that array for what index that is, you'll discover that there was 124 characters before, or values before we hit that value. Plug those in, and that's your answer. And that's it. So because there's no real because it's just basically maths that gets us to the final answer. The only overhead in the time that it takes to actually run it is just how long it takes to run a few of the simulations. In that case, it took just under 2 seconds. I could speed that up. You can make that better, but you don't really need to. It's kind of fine. And it gives the right answer. It's even faster for the sample. If I just let it run for the sample, it's pretty fast. Milliseconds gives you the right answer. And that answer, and it won't take any longer than that really to compute. It's because it doesn't matter how big it is, as long as you know that you've done enough iterations to find what you're fairly certain is that repeating pattern, then you're okay. They could make this harder by that repeating pattern having nested repeating patterns, in which case you'd have to go really long to make sure that you're 100% certain you have the repeating pattern in it, and also visually by eye trying to spot that repeating pattern would be much harder. So yeah, that is it. I hope that makes sense. It's a fairly difficult thing to do. Having seen it, even though I knew exactly how to approach this problem, I was tripping myself up with the logic of trying to figure out the offsets and then also trying to identify what the pattern stuff was. I'm sure you can do this clever. I think you can look at like when the cache stopped filling and look at that number and see is that the number of full iterations, and then that would at least give you the offset value. But then the length of the repeating pattern you'd still have to determine somehow. But yeah, it'll at least give you a place to start anyway. So still some manual work in this. I'm sure other people have done this without manual work, but this is how I've approached it with some manual work. So yeah, that's it for today. Well, maybe I'll see if I can solve 12 part 2 today. You might be getting a third video today, but if not, I'm not going to break myself trying to solve that 12 part 2. And if not, I'll see you guys tomorrow for day 15. Hopefully it's a bit easier than the last few days. I feel like 12, 13, and 14 were all pretty hard days. So maybe we're due for a nice easy one just to let us reset a bit. And then maybe I might get 12 part 2 done. Who knows? Anyway, thanks for watching, folks, and I will see you guys in the next one.